topological symmetry plus C4 point group symmetry. And with these two symmetries, he proved that there is a topological insulating phase distinct from the trivial band insulating case. And there are two important features in this case. Although one should notice that it is simply a spinless model. This is, well, so this is unfortunately why this kind of system is very difficult to find in reality. But anyway, this is a very important example because the first important feature is that in order to get into topological phase, okay, there is no need to apply a spin orbital coupling. Okay, this is not a necessary condition. This is very important. Although so far the topological materials we have found, all of them need spin orbital coupling, but here in principle we don't need spin orbital coupling.
But this is specially designed Hamiltonian, right?
This is specially designed Hamiltonian in the sense that you see, if the system possesses C4 symmetry, then its one-dimensional representation actually have 4 eigenstates. But here, it's very spatial because we assume we simply keep two of the 4 eigenstates, and the other 2 states we simply assume they are high energy states, so we can get rid of them. Okay, so I agree this is artificial, but I want to say in principle people may have hope to find out a non-trivial topological insulator without a spin orbital. And the second thing is that, okay, now its surface state doesn't look like a Dirac spectrum. As you see, it's not just just linear with linear dispersion, but here with quadratic dispersion. Why quadratic dispersion is interesting from theoretical point of view? Because as we can see, in this system actually it has quadratic dispersion, and therefore the density state at this closing point is finite. Why this is significant? Because unlike Dirac system, which has 0 density state, but here with finite density state, so if one can turn on even small perturbation, this surface state may lead to non-trivial many-body order phase. So this is very interesting in this sense.
I wonder whether C4 is special. Any uniaxial point group can have this kind of...
actually, there are more.
C4, C6 or C2?
C3, C4, C6.
Okay.
In many cases, you can have...
so any uniaxial point group should be...
you mean trivial?
To create such a so-called TCI.
Yes, but I will refer you to check Dr. Chen Fang's paper. I can show you later.
Okay.
But today I'm not going to explore all these topological crystalline insulators. Today I'll focus on topological crystalline insulators protected by mirror reflections. Okay, so as I said, today I'm going to focus on this topological insulator with mirror symmetry. Well, okay, so the idea is as follows. let's consider a system. This is its first Poisson zone, and it has a very simple cubic shape. And also, we assume it has some mirror invariant planes. And here, clearly, we have a plane. If this is KZ direction, okay, we assume so we can see we can have a mirror reflection plane here, or on the top. Now, why on the top is okay because it's periodic on the condition. But suppose the low energy physics simply occurs at KZ equals 0 plane. Okay? So let me simply focus on this mirror. It's auto beta.
应该是快没电池了，把它贴过来。
有点接触不了。Okay, I'll try my best. Okay. Okay. So now, if we consider this mirror plane, and also, and therefore the momentum is indeed this momentum space, right? Momentum subspace. And therefore, we know this mirror symmetry actually is commute with the Hamiltonian. Okay, and since M is commute with H, notice that the momentum means only momentum in this mirror plane. So you can block diagonalize this Hamiltonian. Okay, and this M, because we know with spin 1/2 system, M squared equals to -1. So in this system, you can have a block with mirror eigenvalue plus I. Okay. With mirror eigenvalue plus I, and the other one is minus I. Oops. Okay. And why introduce extra crystal symmetry can give you more non-trivial topological phase. That's because if you add on more symmetry, then you will get more non-trivial representation for your system. So here is an example, right? So if you block diagonalize your system into, say, 2 blocks, and these 2 blocks, there are at least 2 possibilities. Here is just only one possibility, but in general, actually, for each block, you can either have, the black Hamiltonian. Okay, the black Hamiltonian. So you have a Hamiltonian, looks like that, and you black diagonalize it. So you can have 2 possibilities. One is each block has the same symmetry as the original edge. And the other possibility is they do not possess the same original symmetry. So here is an example. If we do have this one and this one with eigenvalue plus I minus I. And here, you will see each block breaks time resistance. Although the total system is still preserved time resistance symmetry. Okay. So they belong to class A. This class A, well, is some terminology. You can simply say they are in the same class as integer control. Okay. Integer control is also class A. Okay. So you can, for each block, you can compute its chain number. Okay. So this means chain number within block I. This is chain number should have opposite sign. And therefore, in this case, although total chain number is still 0 again, because of tangential symmetry, but you can define another new topological number, call it the mirror chain number. That's because we consider the chain number within this mirror plane. Okay, and so we can define this index. And what's the consequence of that if this number is non-zero? Okay, we can go back to the example in integral. For example, if we consider n equals 2 on the whole system, and you know the consequence is that at certain age, okay, if you focus on one certain age, you will see two Geber's property modes. Okay, they connect different Landau levels, or say from connect balance band and exponential band. So now, how about non-zero mirror chain number? Okay, if we consider we know the mirror plane. Mirror plane. This is a mirror plane, and if now we have a boundary, we consider a boundary plane which is perpendicular to this mirror plane. For instance, I consider the plane here. Okay, if I observe this open. Consider this boundary. Then the consequence is that very similar to quantum Hall system. For a block with eigenvalue I, mirror eigenvalue I, suppose it's 2. Then it simply means you will find out two boundary modes, just like quantum Hall system. And for the other block, you have another index minus 2. Then again, you have two boundary modes, but now the problem duration is different. This is because they are simply constrained by the time resistance symmetry. So that's why in mirror symmetry protected topological insulator, if you consider this plane at this mirror plane position, you will find two Dirac cones. This is simply, this one is one Dirac, the other. Okay, so again, I give you a real example in the real world. So this material is discovered in, I think, 2012. Kitera. Actually, it has been predicted to be a mirror symmetry protected topological insulator. Also, you can view it as one of topological crystalline insulator. It has a rock salt crystal structure, and this is its first proposal. One thing, this is not very clear here. Actually, it should be a colorful plane, but I don't know why it just disappeared. But anyway, this is the mirror plane. You can have one of the mirror planes you can have in this system. Okay, so you will pass two non-equivalent L points. And if we also consider a boundary, which is 001 surface, then we can see there are surface Dirac cones. This is 001 surface. So I should emphasize again, the box symmetries says first time reversal symmetry, second inverted symmetry, and finally the most important one, because the Dirac cone surface state is actually protected by this inverted symmetry. And there are also more relatives of this material. Basically, they are all 4-6 type semiconductors. Either you replace tin by lead, or you can replace tellurium by selenium. Of course, they have been confirmed by Abbe's experiment. By Abbe's, it's a simple way to see if there are non-trivial surface states. And as you can see, all this system, say the original one, Terabyte, it has property of Bond gap 0.2 electron volt. And we say it's a p-type topological crystalline insulator in the sense that in usual case, the Fermi level is actually below the Dirac cone. And this is because the existence of T vacancy or defect in the system. But this experiment is very difficult. Why very difficult to perform? Because for tinterite, usually you will form some orthorhombic structure instead of Roxon structure, very cubic, not very cubic in usual case. So you need some detailed treatment. So people want to improve this situation, then they can try to replace tin by some other elements like lead. So if you replace tin by lead, at a certain level, you can even tune the chemical potential to revert p-type to n-type. Okay. So this. Okay. So then, in this sense, it's better than the conventional topological insulator like bismuth selenide or bismuth terabyte, because in that case, it's very difficult to tune chemical potential. But here, you can simply use element substitution. Use this way to tune chemical potential. Okay. I think I should speed up. So next, this is I think this is today our focus. I think that means in mirror symmetry protected topological insulator like Terabyte has non-trivial Dirac cones, 001 surface, and I think there are 3 points. There are 3 features I think are prominent. First, it has even number of Dirac cones. This is quite different from the usual topological insulator where there's only one Dirac cone at gamma point. And if you use conventional Z2 index, then what you see is that this system is simply trivial because its Z2 index is simply 0. However, we know this system actually its mirror chain number is plus 2 or minus 2. So it's not 0. But the consequence is that now the Dirac cones must be even. And the second thing, also very remarkable, is about its orbital character. It has very different orbital characters above Dirac cone or below the Dirac cone. Okay, so this is a schematic diagram. As you can see, above Dirac cone, for the outer range, you do have a tin with PZ orbit, but below Dirac point, for the outer region, you have tellurium PX orbit. This is a schematic picture around this X point. Okay, so this is the second thing I want to mention. And the third thing is that there exists a Lipschitz transition in the surface state, in the sense that if you lower the energy in your system by changing photon energy in objects experiment, actually people do observe that the Fermi surface evolves as a function of energy, as a function of constant energy in the electronic system. As you can see, the starting point is Dirac point. The Fermi level is here, and you see two Dirac points. And when you shift your chemical potential lower and lower, basically what you see is the Fermi surface changes shape at a certain point, we call Lipschitz point, here. And therefore you have two separated Fermi surfaces. Now you have connected point. Okay. So why this is important? I think this is important in the following sense, because in this case, the Lipschitz point is actually a set of points of a system. And as we know, the set of in this system actually we have four equivalent set of points at the Lipschitz point, and it's significant because you know, as a set of points, the density state is actually log divergence this point. Therefore, if we can tune chemical potential nearby this point, then you can expect a new orbit symmetry metabolic state can happen. So this is a very interesting system, and need to be explored more later. And this is just give you an example. Actually, we got similar situation in graphene. If you heavy dope graphene to 3/4 or electron dope or whole dope to 1/4 feeding, then actually it leads to trivial superconductivity called chiral superconductivity, D plus I D. Okay, and there is another feature. Another thing in this system is that there is you can study topological phase transition in this system by simply replace T by lead. Okay, here I just show two simple band structures. Here for T-telluride, you have inverted band, as you can see here. You have red dot in the conduction band. But for laterite, what you have is red dot only in valence band. So this is band inverted phenomena occurs only in T-telluride. So as you can expect, if we can tune or we can do this element substitution, increasing the concentration of lead, then we can tune from trivial band insulator to non-trivial topological crystalline insulator. And of course, there are more ways to do that, and we can even we can do chemical substitution. We can increase energy, make thermal fluctuation, or we can simply break mirror symmetry. It can also lead to certain topological phase transition. Okay. Finally, here we provide some theoretical and experimental study for this Dirac surface state. For theoretically, actually, we can develop a simpler K-dot-mean model to describe the surface state. In the pictures I showed you earlier, they are also done by first principle calculations. But in order to understand its physics easier, actually we need some simplified model. So this one is we developed for that surface state. The basic strategy is that we consider the symmetry of this and using this mentioned symmetries and mirror, and we can actually develop a simple full band model. And indeed, we can characterize several important features for this surface state. First of all, in this model, we can easily understand why there is no auto-plane spin component. This is because of two mirror symmetries, MX and Z and Y Z, and tangential symmetry. And also, it helps to understand mirror chain number by understanding its spin texture. And also, okay, this orbital character is actually our input, so I just want to emphasize it again because it is related to later experiment. Okay. So this here I draw the spin texture of this Dirac surface states. What you can see is that with different mirror chain numbers to different sign, then you can have different types of spin texture. But basically,
do you include spin orbit coupling in your model?
Yes.
Indicate.
Yeah.
Before you say spin orbit
we
coupling,
need spin orbital coupling.
So
actually, 4-6 type semiconductor has large spin orbital coupling.
Yeah. Okay.
Yeah. So that's of course we need spin orbital coupling.
But I mean, it's essential because in the middle of your talk you mentioned that the spin orbit coupling is not essential.
Okay, so this is a very important point. I want to, I want to emphasize that because nowadays when people talk about topological crystalline insulators, they usually somehow mix up these two. From my point of view, is very different things. Okay, one is discovered by, actually these two are all predicted by Liang Fu, so people always cite his papers together. But actually, I think one is for spinless model. Okay, this is that's spatial because it's not necessary to have spin orbital coupling, and its dispersion is not Dirac-like. I mean, surface state is not Dirac-like. But the other one is this mirror symmetry protected topological insulator. We also call that topological crystalline insulator, but here we need spin orbital coupling. Okay. But so far, if we doesn't include any exchange coupling, electron-electron interaction, then there's so far I don't see any topological insulator without spin orbital coupling. Okay.
Maybe I ask you another question before I disappear for lecture. Why can't you call this wire fermion instead of Dirac fermion? Because these are, I mean, like chiral spin texture and the spin are not degenerate. For more rigorous definition, I should call this wire fermion. Okay, so